In the previous lesson, you learned how to express the uncertainty of an instrument. You also learned how to explore the errors in your experimentation, to be reflective about the experiments that you're doing, and to identify the type of error that you might be getting. Now we're going to start putting these two ideas together. Today we're going to define something called absolute uncertainty, fractional uncertainty, and percentage uncertainty. Because as you start taking data and analyzing it, you have to process the uncertainty to take into consideration the calculations you're doing with the data that you're measuring. Then you're going to calculate the uncertainty in the situation where you take repeat readings, right? So for example, if you work out an average time. You're also going to learn how to distinguish between an instrument uncertainty and a repeat reading uncertainty. That is, the uncertainty of your instrument and the uncertainty that happens because you're taking an average. It will make more sense once you actually do it. Let's go back to the original slide where I introduced the idea of uncertainty. The absolute uncertainty is that original reading, the one you take from the instrument. Note, the units of the uncertainty are the same as the units of the reading and must be expressed in that way. That's what makes it absolute. They're both in the same units as your measuring device. Your fractional uncertainty is when you start taking that absolute uncertainty and doing some fancy stuff with it. We're expressing it in terms of the original reading. We want to see how big that uncertainty is compared to the actual object we're measuring. So to calculate the fractional uncertainty, we work out the ratio of the uncertainty to the original measurement. So you divide 0.1 by 1.2 seconds, and that gives us our fractional uncertainty. Calculating the percentage uncertainty is pretty much doing the fractional, but taking it a little bit further. The percentage uncertainty is calculated by dividing the absolute uncertainty by the measured value and multiplying it by 100. So you take the absolute uncertainty, divide it by the measured value, but multiply it by 100. Yes, this is actually the fractional uncertainty. So you can just as easily just take the fractional uncertainty and multiply it by 100 to give you your percentage uncertainty. In this case here, it would be 0.0625 times 100. Just test that this has made sense to you. If the measurement on this ruler is 49.0 plus or minus 1 centimeter, quickly work out the percentage uncertainty and check your answer. Stop the video now. Hopefully you got the same answer, 1 divided by 49 times 100, which gives you 2%. Okay, so that was easy. Let's throw something else at you. Now I'm going to explain how to take the uncertainty or find the uncertainty when what you're doing is repeating results. Now the first question is, why do I need another type of uncertainty? Because our measurement in uncertainty is telling us what range of possibilities lie within our measurement. It's telling us that our instrument is not infinitely precise. It's not going to give us the exact to a millionth of a decimal place. It's providing us with a numerical value for that uncertainty. But now we're going to think about things completely differently. If I measure the swing of this pendulum, if it was a real pendulum that is, and so therefore not doing the same thing over and over. If I measure the swing of a pendulum, I'm not going to get the same result each time. And that uncertainty in my measured value has got to do with a whole range of situations. Could be wind currents, temperature changes, all kinds of bizarre reasons. Could be my reaction time. It could be the way that I'm the attitude I have towards the experiment. Anyway, there's a whole bunch of reasons why when I measure the time of this pendulum, I'm not going to get the same answer. So now I need a different kind of uncertainty measure. I need the measure from my ruler or my stopwatch in this case, And now I also need a measure of the uncertainty in the way I'm doing the experiment. Now, if I take a bunch of readings and they're all exactly the same, then it's obvious that I don't need that uncertainty. Here we have a range of values that have been measured for speed. As you can see, the first reading was 1.24, the second reading was 1.92, the third velocity or speed was 1.34. So basically, something is happening in this experiment, which means that this result is not the same. So there's a new extra type of uncertainty. So the way that I calculate that is I take the maximum and minimum values in that range, which is 1.92, which is the maximum, 1.24, which is the minimum, and I divide that difference by 2. That gives me a new range, 0.34. And this is how I express the uncertainty in the velocity. I can do it again here. My largest number is 1.93. My smallest number is 1.74. I would subtract 1.74 from 1.93 and divide it by 2. That would give me my uncertainty in this set of values. So in the end, you would end up with a new column with average velocity, average uncertainty in meters per second. Don't forget the units for uncertainties. Now, in the end, you do have to decide which is the relevant uncertainty. So what you would do in the end is compare your uncertainties in this column with your uncertainties in the instrument section, and you would decide which one is more relevant, which is the greatest one. The largest uncertainty wins. Try this question to see if it makes sense. The time taken for a ball to fall from the top of the Eiffel Tower is recorded 3 times. So you've got 3 different measures. What would be the random error and what would be the average time? Stop the video and give it a go. Right, the answer is A. Now, it's a good time to talk about significant figures here because that's very relevant. Your data has 3 significant figures, and more importantly, in this case, 2 decimal places. Your final answer should not have more decimal places than the original data. So therefore, these are not valid. 7.73 is too many significant figures, too many decimal places, and so therefore this cannot be valid. It must be 2 decimal places. 2 decimal places. Now, the answer using the range of values is 0.185, but your uncertainty cannot have more decimal places than the original answer. So you must round it up to 7.77 plus or minus 0.19. Uncertainties are limited to 1 or 2 significant figures. The uncertainty cannot be more precise than the best estimate of the measured value. So this column here, your uncertainty should never be more than your actual values. Okay? Now, the last point. How do we lay out our tables when we're doing experimentation? Well, your independent and dependent variables will be placed in separate columns. But at this stage, and I'm not going to go into more complicated ideas such as raw and processed data, I'm just going to talk about uncertainties. You must make sure that you have a section which expresses the uncertainty, the instrument uncertainty. And if you're taking repeat readings, you can express it as a split cell here, like that, over the 3 different readings. Make sure that you have units for your uncertainty and your reading. So you always express the units of the uncertainty. And your average will also have an uncertainty average. This is just one way of expressing uncertainty. Delta V. Delta stands for the range of uncertainty. So that's just shorthand for uncertainty. But note that it also has units.